Okay, so now we have a problem, right? So our B is the right-hand side. And now from now on, let's delete our X and we pretend we don't know the exact solution. We want to use an iterative method to solve that. So Jacobi and Gauss Seidel. We have learned that, so for just as a reminder, for Jacobi, right, we are having the D times X at the K plus 1th iteration plus L plus U, so the lower and upper diagonal component of the matrix plus xk is equal to B. For Gauss Seidel, so this is Jacobi. For Gauss Seidel, we have D plus L times xk plus 1 plus U times xk is equal to B. This is Gauss Seidel. And in implementation, this is not how you implement. You don't actually construct the matrix, and you don't actually invert these matrices. What you do, for example, for Gauss Seidel, for the two-dimensional Laplacian problem, is that you write the Laplacian differently. So here, the Laplacian is x of I minus 1j plus xi plus 1j plus xij minus 1 plus xij plus 1 minus 4 times xij is equal to bij, right? And then if you loop over the rows and columns of this grid, you just put superscripts, what iteration number you're on these individual grid points. So for ij, which index are you putting, k or k plus 1? K plus 1, because it corresponds to the diagonal component. For this one, it's the future, right? I haven't iterated to j plus 1 yet. So this is what? K, right? This is the explicit term. How about this? J minus 1 is something I already iterated. So it's k plus 1, right? And this is k plus 1, right? We'll just, but in terms of implementation, we just pull this part out to the left-hand side. Everything else is already computed. So the algorithm would be xij, k plus 1 is going to be, okay, if you move everything to the right-hand side, b becomes what? B becomes minus delta x squared over 4. I'm basically dividing this out, times bij plus just the 1 over 4 of all the x components of all the neighboring grid points, right? This is I minus 1j, I plus 1j, ij plus 1, ij minus 1, right? Okay, so let's implement this again into MATLAB. So I'm going to write another function called Gauss Seidel. And the input is, I want my initial x, I want an initial guess, right? I want a b, and I want the number of iterations. Let me just say n iterations. So my output is my x, is my new x. Okay, so first of all, we loop over the number of iterations. And what do we do? Pardon? Yes, I loop over I goes from 2 to, oh yeah, I need to also compute the number of grid points is again equal to size of x in the first dimension minus 1. And dx is equal to 1 over n. Okay, so I and j are both from 2 to n, and my x ij would be here, right? So I have minus dx squared over 4 times bij plus just the average of the surrounding grid points. J plus 1. All right, I think that's it. And x new is equal to x. Any questions? So let's try to see if it works. Let's initialize our x to zeros, 4097, right? And let's call x equal to Gauss Seidel, not Gauss design, Seidel of x, b, and 10. Let's do 10 iterations. It's doing the work. All right. It's not returning instantaneously. Okay, it's completed. So let's see what our solution is. I am sure of x. Black. Okay, actually on my screen I can see a little bit of lines, but like the projector is not good enough. So let's actually multiply by 100 to let you see what we get. So this is what we get. It kind of shows a little bit of the features of the solution, but it's far from the solution, right? You have to magnify it by 100 factor to get this. And particularly if you just look at, if you compare the error, the solution error, which is x, actually the negative of the solution error, x exact minus x, like how far we are away from the exact solution, right? It's almost the same as the exact solution. And let's actually compare it side by side. X exact. So first of all, we see that Gauss Seidel 10 iterations is doing almost nothing. And then it's actually interesting to zoom in, right? So from here, it's such a huge image. You don't really see the details. So let's zoom into the tail. So figure 1 is the remaining error, and figure 2 is the original exact solution. You see the difference? What have the 10 iterations of Gauss Seidel done? You see any difference between these two tails? Yes? No? The left one is blurrier. Yes, that's right. So this is why this kind of observation is the motivation of actually multigrid. So last lecture we have seen that as you increase the grid size, the Jacobi iteration becomes slower to converge. The same thing is actually for Gauss Seidel. Gauss Seidel converges usually around twice as fast as Jacobi, and when Jacobi slows down, Gauss Seidel slows down. But the observation here is that if you apply Gauss Seidel or some small variation of Jacobi for, let's say, just a small number of iterations, the solution error becomes blurred out. Right? The original solution error is actually the exact image because it's just the solution initial guess is zeros. After 10 iterations, the solution error gets blurred out or gets smoothed.